So we've spent one class trying to figure out some rudiments of matrices, matrix algebra, right? Linear algebra. Subsequent to our first class, this one class, we'll explore a few very potent properties related to matrices. The first set of properties related to adjoint of a matrix. An adjoint obviously pertinent to square matrices alone. Square matrices, let's say, of a certain order, n. And like I told you in the last class, adjoint of a matrix is the matrix of cofactors transposed. Matrix of cofactors transposed. Did I also share with you the property A adjoint A is determinant A into IN, identity matrix, right? That has been discussed, right? A adjoint A is determinant A, which is a number, a scalar, into IN. IN is an identity matrix of the same order as A. N is the order of this identity matrix. Have I also discussed adjoint AB is adjoint B into adjoint A? Have I discussed that? Right? Which is the rule of reciprocals. Reversal, not reciprocals, reversal. Adjoint AB, A and B are two square matrices of the same order. Adjoint AB is adjoint B into adjoint A, which is the reversal rule. And the reversal rule also applied for transpose. AB transpose is B transpose into A transpose, right? The reversal rule applies for adjoint AB, which is going to be adjoint B into adjoint A. And not just this, it could be generalized. It's like using this, we could establish adjoint A1, A2, AK is like adjoint AK, AK minus 1, sorry, adjoint AK, adjoint AK minus 1, adjoint A1. That's the rule of reversals. That's the rule of reversals, right? Now, let's look at yet another property, adjoint of a matrix A power M. A power M means A into A into A M times. Matrix A multiplied M times, right? That's the same as adjoint of A to power M, right? Now, a very direct consequence of this, adjoint A to power M is like adjoint A into A into A into A into A M times. Yes or no? Right? A1, A2, A3, AK minus 1, AK kind of a thing. Yes or no? Right? Which is now using the rule of reversals. Using the rule of reversals is going to be adjoint of this A into adjoint of this A, and going this way up to adjoint of the last A, which is M times. Yes or no? Which is adjoint A to power M. So simple, isn't it? Was within reach, isn't it? Huh? So, want to remember this property, adjoint A power M is adjoint A whole to power M. Sounds good? Now, let me look at the next property. K is a scalar, a number. K times A. When I multiply A with K, all entries of A get multiplied with K. This is what happens, right? I want to show that the adjoint of K times a matrix where K is a scalar is K to power N minus 1 adjoint A. That's the next property we'll establish. Have you been able to make a note of this? Shall we proceed? Now, look at this result. adjoint of something. Now, you know, in terms of the most popular result in adjoint is this. A times adjoint of that matrix has a very concrete formation, is determinant A, which is a scalar, into the unit matrix In, identity matrix In. So it would have been a good idea dealing with Ka times adjoint of Ka, because that would have this formation. Ka times adjoint Ka would have been determinant Ka into In. Yes or no? Ka times adjoint Ka would have been determinant Ka into In. Yes or no? Let's start with that formation and see where we are headed. Okay? So replace A by Ka to get semblance of this. Alright? In this identity, replace A by Ka, where K is a scalar. K is a scalar. So we end up getting Ka adjoint of Ka is determinant Ka In. Yes or no? Right? Now, if there is a matrix A whose determinant is this. This is a matrix whose determinant is this, which is a scalar, right? Now, when I multiply A with K, what happens? All entries of A get multiplied with K. Every entry of A gets multiplied with K. So Ka is a matrix. Ka is a matrix where every entry of A has got multiplied with K. Now, see, if I have a certain determinant, say A1, A2, A3, B1, B2, B3, say C1, C2, C3. Right? Suppose I have a determinant this, and if every member is multiplied with K, if every member is multiplied with K here, then I could have taken K common from the first row, K common from the second row, K common from the third row, K, right? So if I multiply every member with K, I have a determinant like Ka1, Ka2, Ka3, similarly Kc1, Kc2, Kc3, yes or no? Right? And suppose this was delta, then I could have taken K common from the first row, K from the second row, K from the third row. This would have become actually K cube times delta, yes or no? This would have become K cube times delta. In general, if I have a determinant of order n, and if every member of that determinant, if every entry of that determinant is multiplied by K, then the determinant will become K to power n times the original determinant, yes or no? Right? So if B is K times A, then the determinant of B would be determinant of Ka. Ka means every entry of A is multiplied by K. Then this will actually become K to power n times determinant A. This will become K to power n times determinant A, isn't it? Determinant of Ka, determinant of the matrix Ka would be K to power n times determinant A, yes or no? Right now? So, good for us. Shall I remove this part? Right? So, determinant Ka, where K is a scalar, would be K to power n times determinant A. So, this would become K to power n times determinant A, In. Yes or no? What's the left hand side? The left hand side is K, A, adjoint Ka. Is this? Yes or no? Hey, but determinant A, In is A times adjoint A, is A times adjoint A, isn't it? Determinant A, In is A times adjoint A. A times adjoint A. Right? Yes or no? And this is KA adjoint KA, left hand side. Right? This K is a scalar. I can divide throughout. It has a thoroughfare everywhere. Right? So when I divide by K, then this will become K to power n minus 1. Yes or no? And this K to power n minus 1 being a scalar, it can invade and intrude. It can invade and intrude. So what really happens here is we need to show is K power n minus 1 adjoint A. You could have written this as A into, now this K to power n minus 1 can get multiplied with this matrix, right? So K to power n minus 1 adjoint A, right? That's an acceptable proposition, right? So I have a matrix A into a matrix B equals a matrix A into a matrix C. Yes or no? It's like a matrix A into a matrix B. This is B, say, equals A. This is A into a matrix C, into a matrix C. Yes or no? And did I tell you in the last class that if A is non-singular, that means if the determinant of A is not 0, and if AB is AC, then B must be equal to C. Don't cancel A for matrices, because A is not a number. A is a collection of numbers. It doesn't have a value. So never cancel A, right? So we then have adjoint KA equals K to power n minus 1 adjoint A. How about it? So that's this property. All's good? Can I remove? Now, adjoint of In is In. In is an identity matrix of order n. In is an identity matrix of order n. We want to show that adjoint of an identity matrix would be the same identity matrix. This is what we want to establish, right? Again, start with this. In adjoint In. In adjoint In. A could be replaced by some In, isn't it? In adjoint In would be determinant In into In. Yes or no? Replacing A by identity matrix In, right? So if I replace A by In, so I get In adjoint In equals determinant In into In. Yes or no? Now, if any matrix is multiplied with I, you get the same matrix. That's why it's called an identity matrix. This is pre-multiplied, and or if I have Pi, that will also give me P. That's the truth of an identity matrix. If multiplied by a certain matrix, it will replicate that matrix of the same order. Yes or no? Right? I times P will be P. P times I will also be P. Now, I times adjoint In, therefore will simply be adjoint In. When these two matrices are multiplied, In being an identity matrix, I times P will be equal to P. Yes or no? So this left hand side will simply become adjoint In and In is what? A diagonal matrix whose diagonal entries are 1 and everything else is 0. And the determinant of a diagonal matrix would be d1, d2, d3, dn. So in this case 1 into 1 into 1. So determinant of In would be 1. Determinant of In would be 1. And 1 into In, that's simply going to be In. Adjoint In is therefore In. Adjoint In therefore is In. In into adjoint In will be a adjoint In. That's a property of an identity matrix, right? It itself gets consumed and reflects the other matrix. This is what happens. Adjoint In, this is 1 into In, which is In. This is what happens, right? So again, a useful property. This I would say is very commonly used. Adjoint of an identity matrix would be the matrix itself. So that's this property. All's good?